suppose that a capacitor or capacitance C is connected across the source. So now we've got a capacitor instead of a resistor. The instantaneous charge Q on the capacitor is given by Q equals capital C instantaneous V. In this case, the instantaneous current is equal to the rate of change of the capacitor charge, so is proportional to the rate of change of voltage. To get the current, we need to remember that current is the rate of change of charge. If we think of the rate of change of charge, that's dQ by dt. We need to differentiate this, and so we end up with minus WCV sine WT. That's the current. You'll see now this is different to the resistance. In this case, the instantaneous current is equal to the rate of change of capacitor charge, and so is proportional to the rate of change of voltage. Taking the derivative of Q, and we've got this. Thus, if the voltage is represented by a cosine function, the current is represented by a negative sine function. If I plot these two curves out, this is exactly what you get. If you plot these out, you'll get this curve here, and then the I curve you'll see here. Thus, if the voltage is represented by a cosine function, the current is represented by a negative sine function, as shown in this diagram. The current is not in phase with the voltage, as you can see. The current is greatest at times when the voltage curve is rising or falling most steeply, and is zero at times when the curve levels off. The voltage and current, as you can see, are out of step or out of phase by a quarter cycle, with current a quarter cycle ahead. The peaks of current occur a quarter cycle before the corresponding voltage peaks. The result is also represented by the diagram of C here. There's the phasor diagram, which shows a current phasor ahead of the voltage phasor by a quarter cycle. So you can see that's ahead of the V voltage by 90. This phase difference between current and voltage can also be obtained by rewriting equation 2, which is this one here, as equation 3. So we can write this equation as this equation. We can think of the expression for I in a capacitor as a cosine function with a head start of 90 degrees. We say that the current leads voltage by 90 degrees, or pi by 2. For convenience of later discussions, I will usually describe the phase of the voltage relative to the current. Thus, if the current in a circuit is given by I equals capital I cosine WT, and the voltage between 2 points is V, capital V cosine WT at theta. If we remember that for a resistor, we got the maximum value was that I equals V over R. Well, we can rewrite this equation here in the same way for the maximum value. Okay, for the I, for the maximum value here, we can rewrite this like that. So we'll just get it in this form, yeah. So we'll go capital I equals capital V maximum voltage over 1 over WC. We'll define a quantity called XC, called the capacitive reactance. That is equal to XC is equal to 1 over WC. You can see that the XC becomes like a pseudo resistor. The SI units for XC are ohms, yeah. So reactance has the units of ohms. The reactance of a capacitor is inversely proportional both to the capacitance C and to the angular frequency omega. The greater the capacitance and the higher the frequency, the smaller the reactance. Once this is very, very large, this reactance is going to get very, very small. Right, here's an example. At an angular frequency of 1000 radians per second, the reactance of a 1 microfarad capacitor, if we can just plug these values in, 10 to the 3 rads per second, 10 to the minus 6 farads, and you get 1000 ohms. So when it's 1000 radians per second, at a frequency of 10,000 radians per second, the reactance of the same capacitor is only, if we plug those in, we'll find it's only 100 ohms. And at a frequency of, so if we lower the frequency even more, find that the reactance is 10,000 ohms. You know, you've got 10 kilo ohm reactance there now. So that's just an example of that, of this equation.